Well, I don't think she's going to move because of Newton's third law, which states that for every force, there's another force equal in magnitude but opposite in direction. And let's look at the situation. So I am applying a force on her, and for my applied force, there is a reaction force applied in the opposite direction but equal in magnitude. As a result, the force net should be zero, and if the force net is zero, there shouldn't be an acceleration on the object, and she would not move as a result.
I am very sure that I will move, because while Newton's third law is true, the forces are acting on different objects. Let's use Newton's second law, which states that force is equal to mass times acceleration. The forces are equal in magnitude, but there is a difference in direction. When the force is the same in magnitude, the object of smaller mass will experience a greater acceleration than the object of greater mass, in the direction that the force is applied. Since there is an acceleration, there is a change in velocity, and there is displacement. Therefore, I will move. Even if the masses were the same, because the forces are acting in different directions, the objects would have the same magnitude of acceleration in opposite directions. Also, a free body diagram is supposed to show all the forces acting on only one object. The previous free body diagram included forces acting on different objects.
You were right. Although the forces were equal in magnitude and opposite in direction, they did not cancel out because they were acting on completely different objects. So in the end, each of the forces act on each of the objects. And I'm sorry I pushed you.
That's okay.
I'm not convinced yet though, because it seems like a heavier object would accelerate more. Because, for example, if I have a rock and a balloon of the same size and I throw them both, the rock would travel further, so shouldn't the rock accelerate more?
Let's test it out. So, we're going to push some water. We're going to be applying an equal force of about 100 newtons to each of these three containers of different masses. The first one is 1 kilogram, then 4 kilograms, and finally 50 kilograms.
And according to Newton's second law, force equals mass times the acceleration, we predict that the smallest water bottle will have the largest acceleration at 100 meters per second squared, the medium water bottle having an acceleration of 25 meters per second squared, and the largest water bottle having an acceleration at only 2 meters per second squared. Let's test it out. From the experiment, we can see that our predictions were correct. Because we couldn't actually measure acceleration, we can only infer acceleration from the final velocity. All three objects were stationary in the beginning of the experiment, and the bigger the final velocity of the object towards the end of the push would indicate that there's a greater acceleration. And for the smaller object, there was the greatest final velocity, as we can see in the video. And the second object had like a medium velocity, and the largest object didn't really move that much.
Just as a disclaimer, the net force will not actually be 100 newtons due to the actions of friction counteracting the force applied. This is why the acceleration would be less than what we predicted. So as you can see, in each one, it was less than this one, barely moved at all.
Now, going back to the question about throwing a rock versus throwing a balloon, the force applied is a contact force. So while the two objects are still in contact with the hand, if the same force is applied, the rock would actually accelerate less than the balloon because it has a greater mass. But once you release the two objects, it's a whole different story now. And the distance that they travel from there will be explained in the next episode of Physics at NAC.